I was curious whether how many students would come today. Write the outline.
So by now the number of offline students has decreased only by 1.
No online students. But okay, I will put it on YouTube.
We have many deadlines now.
Ah, okay, yeah.
So
Do we?
No?
Oh, I have a different program.
Ah, yeah.
Most of my courses are not on software engineering, so I don't know.
Ah, yeah. But I can imagine there are many projects, and then if there are a few together. Lecture. So the topic today is various techniques to prove that a problem has a fixed parameter tractable algorithm. So there will be techniques. The title is so the first will be coloring. So this is a randomized technique we assign. So usually the input is a graph. We assign random colors in some way, and we do something. And so we have a few exercises. Then dynamic programming. And I think this will be an easy topic for you because nothing new. And then what we already know, the branching technique. And so now I will speak about feedback vertex set. So the problem here will be set cover. And then the famous problem is feedback. Okay, you don't know it, so I don't need to write it. Then last time I promised a kernel for vertex cover problem of linear size. So kernels is another technique of size 2k. And then the tree decomposition. Maybe we will not finish everything. but then we just continue next week, and the topic for next week, it will be the last, will be to prove that there is no FPT algorithm. So there exists some theory. Like if you want to exclude the possibility of that the problem is not in P, you can prove it's NP hard or NP complete. And so we can, we have another class, it's called W1, and sometimes you need W2, and you can prove that the problem is the W1 complete, and then you understand there is no FPT algorithm. And so the conjecture here, so for normal computational complexity, you assume P different from NP. Now we will assume FPT different from W1, but it's all the same idea. So but we need to define this for next week, so don't worry if you don't understand anything. But so we will define what is this class W1. It's a bit complicated.
Okay.
And then it's easier to do it directly from exponential time hypothesis. I mentioned it last week. Okay, but this is all for next week. So now we just prove some fun algorithm. We present some fun algorithms, because usually software engineering, it's important to know the techniques, so that when there is a paper and your boss wants to implement it, you already seen this before, and it's less scary. Okay, so we will start with coloring. Also, I barely prepared the lecture, so it will be I'm curious, and now I didn't sleep much, so I hope I will teach a bit slower, and might need some help to remember everything.
Neither did we, so.
Okay, yeah. That's good.
Actually not, but
Yeah. We all have this
for
problem.
the sake of synchronizing the tempo,
Yeah.
teaching and understanding, kind of, yeah.
Okay, so let's start with the coloring technique. So the problem is a k-path problem. So you get a graph and a number k. Can you find a simple path of length k? It means no repeated nodes, simple path. I mean, path is by default simple, but of course if you can repeat nodes, it's a very easy problem. Okay, let me write it. And this problem, it's easy to understand, it's NP complete. So why? It's one of the most famous NP complete problems.
Because it reduces to something like 3 sets.
Hamiltonian path problem.
Yeah.
Yeah. So if k
it is exactly this.
Yeah, if k
Hamilton.
equals the number of nodes, then yeah. So input graph k, the question exists simple path of length. Okay, and so the algorithm. So we want to give, now we're speaking about a randomized variant of FPT, but it's clear what it means. Okay, let us recall what is FPT. So a parameterized problem. Let's call it L. So there are two inputs, the parameter and then a language. Sigma star is in FPT. So if there exists a constant C, a function, a computable function, that's just what we said last. I'm just repeating. And an algorithm that solves a problem in time. And so you remember, that an algorithm that decides times length of x. And so, and there was sloppy, I said to the power c, but the correct definition is length of x plus k to the power c. So I didn't write the plus k here, but for today it doesn't matter.
Why is this different?
I was lazy last time. I want to make things simple to prove a theorem, but I can. It doesn't matter for our discussions.
I mean, why is this different if we can just move the k part to the f? Or we can't?
Oh, so yeah, good question. So if x is equal to 1,
Ну, вообще можем.
well, the thing is that yeah,
Okay, to
yeah, it's indeed, yeah, good point. It's probably the same. Yeah, you're right, it's the same. Sorry. Yeah. Okay.
Could you please explain what is FPT in more intuitive way?
Okay, so if the parameter is small, then the runtime is reasonable.
Okay.
That's the intuition. But the exponent does not depend on the parameter, so it needs to be very reasonable. Like we discussed about the clique problem, we can solve it in time. So for a graph with n nodes in time n to the power k, that's basically n to the power k. And so brute force algorithm is not an FPT algorithm. And next lesson we will see for clique, we cannot hope for better. I mean, it's very unlikely. You can do, you can get rid of the power, the k in the exponent. So this will be unlikely. But for all these, today we will see many problems where we can get rid.
The function can depend on the length of the input and the parameter, right?
So the function.
The function can the function can depend on the length. Then we cannot just erase plus k from, because it's like how do we even do it? It's a Newton binomial.
No, as soon as the length of x is 1, then the plus k can become a factor k. It is anyway bigger, so that's why you're right, it's the same.
As soon as the length of x is...
Yeah, so but we cannot have a length of x to the power k is not allowed in our theory.
Yes. But
But we can have
K-
in the
K-
linear
K-
constant.
k
in the
times
front.
like k times the length of x is it allowed?
So, but this is allowed for us to the power 100. This is okay.
No,
We can't
No,
just
no, I mean-
erase the k, I think.
No, I mean
Well, but I think you're right
because
as
it will be x times something k. Something x times something k.
can we multiply the...
yeah, but you can always put a k to the in the front, a k to the power c. You can always put in the front.
Yes, but all the other k's.
We have like k to the power c minus 1 times x.
So if the
times
length
like
of
that.
x is big, and then we add k, then the length of x can at most double. So we have this to the c, but this is so if length of x is bigger than k, then this is bounded by 2 to the power c, length of x to the power c, right? If we believe this. So in this case, the dropping k doesn't harm. And in the other case, if x is smaller than k, then we're also good. Because we can put the factor 2k to the power c, we can absorb in the f of k. So your comment that I don't need to write k here, it doesn't
Yeah,
matter. It was very clever of you.
Now it's actually
Yeah, yeah.
yes.
I
Yeah.
didn't understand any of that. Not any of that. But I didn't understand before.
Now I see.
But
Yeah, you're very nice.
Do we take small O or big O of this expression type? Big O of f of k times x to the power c, or do we take
It
exactly
doesn't matter
exactly
also,
this?
because you can always hard code a finite number of inputs in your algorithm, so it answers very quickly. Okay, maybe for x, length of x equal 1 and 0. So, but people usually write it like this. But yeah, you can take big O,
Mhm.
and then unless you're very pedantic on inputs of length 0 and 1, it doesn't change anything. Because yeah, just
Yeah,
if you have
okay,
any
okay.
computable function that's so much power.
Okay, it's exactly the same thing.
Yeah, actually mathematically, I should deal with these cases with 0 and 1 input.
We can trust you that they don't matter.
Yeah, it's in the RAM model, you can just in one step check whether the input x is short and give the answer. And so then the runtime is just 1, and then it's fine, and then for the other cases. So usually no Turing machines are used. But we will use circuits in the next lecture as model. So, yeah. They're clever guys who don't bother. Yeah, they're so used to knowing all this theory that they don't bother. Okay, but now it's time. So yeah, but actually a very good point. So there is easy algorithm. We try all k element subsets and check whether they form a path.
Mm.
So that, but then we don't have FPT algorithm because that's this time again. And to the power k, and this is not allowed. So, but the plan is as follows. We will first make a coloring of the graph, but I mean just assign a color to all the nodes. We don't care if an edge connects nodes of the same color.
Mhm.
So we choose k color and randomly assign colors to the same node, and then we check whether there is a path in which all the nodes are numbered. So the first node that has color 1, the second node color 2, 3, and so forth. So for example, was the next the usual graph, and then we want to know whether it has a path of length 3. So we already know the answer, but just to illustrate the algorithm, then we will generate 3 random colors. So I will use 1, 2, and 3 for the names of the colors. And so when we generate, it might be something like this. And then we check whether we can build a path with the colors 1, 2, 3. So we want to find whether we can find somewhere in the graph this thing here.
Mhm.
And this can be done, yeah.
The amount of colors is k.
Yeah, yeah.
Mhm.
And so the question is, how do we know that we can do this in polynomial time? Check that there exists a path like this.
Mm.
So for this we rewrite the graph in 3 sets. So we will make all the nodes with color 1, all the nodes with color 2, and all the nodes with color 3.
So we can just run DFS from each
Yeah.
vertex. But if we assign the colors randomly, we can get a graph that contains only, for example, color 1, so 1, 1,
Yeah.
1, 1, 1, and it's a problem for us.
Yeah. So the plan is to do it many times and
Okay.
prove that if we do it enough, then it will be okay.
Okay.
Actually, will be.
Yeah.
Okay.
So imagine that our graph indeed has a path of length 3. So let's pick one path, we assume it exists.
What is the distribution of color?
So
on a given
uniform,
node?
every node gets uniformly
Uniformly
so-
distributed colors.
yeah.
And how do we prove that?
Some question before we begin. Can we do it without random, but just invent some simple deterministic algorithm for assigning
So we
colors?
can de-randomize, but whether it's simple,
No,
it's
but we can do it.
yeah, we can make it deterministic. I will quickly tell you how
Okay.
it goes.
Okay, good.
Okay,
The idea is clear.
yeah. So now, what is probability that we will indeed find? So you get how I build this graph.
Mhm.
It's very yeah. And so now probability of find the path over the colors. And so I claim that this is 1 minus 1 over k factorial. So do you see why? So if we do it once, yeah, it's more than 1 over k factorial.
Probability of what? Probability of
Probability that we are lucky and that we find the path.
the probability of some step.
Yeah. So we do it once,
Okay, I see.
we assign once random colors,
Yeah.
and then what's the probability that we do have a path?
Do we assume that the graph contains the path?
Yeah. So we
Okay.
at least
so,
one
so,
path.
so, so if graph contains a path, okay, so and we are only looking for paths like directly, like the first node must be 1,
Yeah.
the second node must be 2. Okay,
Yeah.
so
It works even for directed graphs. This,
So we have this path, and we multiply the probabilities that each of the vertices will get the expected color. So
yeah.
one
sorry,
divided by
I'm wrong. Yeah. You're right. So we have k to the power
Yeah,
k.
yeah.
Yeah. My mistake.
so the probability that the first node gets color 1 is
Yeah.
1 over k.
Yeah.
No, because it could have gotten
Yeah.
one over k colors. The second node as
Also
well,
1 over
is
k.
also,
Yeah.
and the length of path is k, so it's
Yeah.
1 over k. So okay.
And so now we know how many times we need to do it before we get 1/2 probability of luck, or 1 over e probability to be lucky. And so probability that we fail.
We need to take log k to the power of k,
Yeah.
k log k.
Probability t failures is equal to 1 minus probability that we are lucky in a fixed time, lucky first time. Let me write it again. So this 1 is equal to 1 minus probability lucky first time to the power. So if we have t iterations, t colorings, t random colorings, we get this thing, right?
you forgot to put the closing bracket.
What do you mean lucky first time?
Yeah,
Uh,
because
what
the
does-
probability we're lucky the second time. I mean, we find path first time. So lucky
Right.
means find path the first time. So this is probability we fail the first time times probability we fail the second time times probability we fail and so on. Okay, so what is algorithm? What will be algorithm? We will set t equal to k to the power k, and then we try k to the power k colorings. And so what is the probability? We have k to the power k failures. It's probability that we fail the first time, times probability the second time failure, third time, and so on. And so when we have t attempts, we multiply all these probabilities, and in each attempt the failure probability is the same.
I didn't quite get it. What are we doing?
Yeah.
Can you please repeat?
Yeah.
From there, like the
okay.
probability of finding
Yeah,
a
we
path
want-
given a random coloring, it's
I
easy.
want to prove that this is e to the power exponent minus 1. Probability that
Exponent minus one.
that we have t failures is smaller than exponent minus 1. So
The probability of not finding a path, given that it exists in the graph after trying t times,
yeah,
given
and
assigning
just
random
solving for
colorings.
t. Yeah.
And so we set like t to the k to the power of k.
Yeah.
So
And we
we
try to get
want
And
to
now-
find when the probability is equal to 0.5.
Yeah. And so here we use exponent minus 1, so that's even a little bit is smaller than 1/2. Okay, and now we use formula that says 1 plus r is smaller than exponent of r. And so r can be positive or negative. It's some famous formula. Should try to remember this. It's
Okay.
and everywhere.
We believe.
Especially for cryptography, yeah, you also have probabilistic algorithms. No, it's easy to prove. So first, exponent Taylor expansion starts with 1 plus r. So you can see that it's for sure on when r is positive it works, and when r is negative, you can compute the derivatives of both sides. So derivative will be 1 here, and here it will be exponent r, and r negative. Okay, then you need to think about derivatives. It's easy also. So we will apply this. So okay, we know that probability to fail. So probability to find path is bigger than 1 over k to the power k. So we have probability to find, so fail one time is 1 over k to the power k, which is, so let's use t, which is smaller than exponent minus 1 over t. And now we take to the power t both sides. So here we take to the power t. So this is equal to exponent minus 1. This is precisely what we want. So here probability of find path is 1 over t here.
Why do we write first time on the bottom? We shouldn't, like, we should write 1 minus probability find path, right? Right here. I mean, in these brackets on the left, find path, and then we write first time. What does
1 minus find path at the first attempt. So
What
here we
does-
speak about t attempts.
We what
For
is
the first coloring.
what is an iteration? We assign
One
we
iteration.
assign a coloring, and
Yeah.
then we check all possible
Yeah. That's one equation.
so like why first time on the
Yeah.
on
So
the,
it is probability that we fail.
yeah, I got you. So we exclude как-то условные вероятности.
Yeah.
Conditional probabilities.
Yeah.
So we say that our events are independent.
Yeah. Exactly.
Assigning colorings are independent
Yeah.
events,
Yeah.
and so the probability is always 1 over k to the power of k, and we like t times to the left is this, to the right is exponent minus k to the power of
Oh, by the way, I
Uh-huh.
printed exercises.
okay.
So there are several about coloring.
We got
Yeah,
formula.
sorry.
Formula.
So there is exercise with triangle packing, but just if somebody.
However, this example with 1 minus 1 divided by t is not our case because
So here probability is at least 1 over t. And so I'm trying to make a lower bound that we all fail.
okay.
Yeah, sorry for the different places on the board. It's not. So we want to bound this by. Okay, let me write it nicely then. In one chain.
So you mean if we do k in the power of k steps, we will achieve what
Yeah.
we need.
And this is smaller than exponent minus 1 over t times t. It's exponent minus 1. This we already understand. Is exponent minus 1, and this is smaller than 1/2. And if you want 1/4, then you just do it 2t times. Okay. And so what is the total runtime of our algorithm? It's t times poly n. So it's equal to k to the power k poly n.
So this is acceptable. K.
So
to
it's
the
enough
power
for
k
this
is
definition.
a
Yeah, after the-
computable function.
Yeah, yeah.
Yeah.
So now you know the coloring
My
technique.
problem is that at the beginning of the course I didn't understand the definition of computable function completely, so it's given in the book, CIPSA book, but
Yeah.
I still don't
And
understand.
just the Turing machine exists that computes and
Okay.
halts, always halts,
Okay.
and then give the
I see.
correct output. Like halting problem is not computable.
Given only the input on its tape.
Yeah.
Started with only input to its tape, always holds with the proper
Yeah.
output.
But then you think about a RAM machine, but it's related to runtime with within a polynomial.
Do we have some non-computable functions?
Yeah, the halting problem.
I-
Yeah.
Yeah, I mean,
Or the Busy Beaver function. It's like given a k, the runtime of the slowest program of length at most k on a Turing machine.
okay.
Yeah. There are people who compute this function as hobby, and it goes very, very fast. Yeah, I was also like overworked. I said, okay, I will try to compute it, and it's actually nice to do because there is this Collatz conjecture, and it's like very easy. So to build a tiny Turing machine that checks this Collatz so this you get a number. If it's even, you divide by 2, and if it's odd, you multiply by 3 and add 1. And so the question is, if you start with any number, will you get down to 1 positive number? Will you go down to 1? Because 1, it gets in a cycle. It goes 1, 2, 1, 2, 1, 2. And so it's extremely difficult problem. So it's open question whether even the set of numbers that go down to 1 is decidable. So nobody knows. And Erde said that no point to work on it. Mathematics is not ready for this question. and so yeah, he's a very famous mathematician. He died in the 80s, late 80s.
Why in poly n we can decide
Poly
it's
n, it's the
certain
time to check that first search.
Yeah. I mean, but it will still be a probability.
A probabilistic algorithm.
Probabilistic
Oh yeah, there
algorithm,
was a
yeah.
question. I almost forget. So how can we make it deterministic? And so what are we using to compute the probabilities here? We only need k-wise independence. So when we write down this probability, we don't. So the plan is to use hash functions. So k-wise independent hash functions. And why can we do it? So that's the only probability we need for the given coloring. So we don't need that all the colors are independent. We just need that any set of k points have independent colors. So if we look to any set of k points, we need them to be independent to get this, because we only multiply. So do you know the difference between independence and pairwise independence, for example?
Mm-hmm.
Okay, so if I take two random bits, I have two random coins, and I consider 3 bits. So coin 1, coin 2, and the XOR of the 2 coins. So then these 3 variables, they are not independent. What I don't need to worry about what I'm explaining now, it's just background information, because somebody asked how do you make it deterministic. So okay, if you have, but it's very important concept. So these three bits, they are not independent, because you cannot make 1 1 0. No, 1 1 1 you cannot make, because the third is the XOR of the other 2.
Yeah, the third is.
Yeah, so it's definitely not independent.
Yes.
But if we take any 2 bits, they are
pairwise independent.
Yeah, they are independent. So if we take, of course, the 2 original coins, they are independent. But the first coin and the XOR is also independent.
Because the XOR is actually just adding a second coin.
Yeah,
which
so
is-
yeah,
which
it
was
means
independent.
you take one coin
Yeah,
and you look at the inverse of the other coin. If it's 1 and the original, but yeah, they're basically equal.
Mhm.
Yeah. Or yeah, I should just say, I take a copy of the second. I don't know. Then they're not all pairwise. Okay, yeah. So so we need to XOR. You cannot
If
take
the random variables are pairwise independent, it doesn't mean that they are altogether
Yeah, yeah.
Oh, okay.
And so what's our plan is that with hash functions, that's typically you use them when you only need pairwise independence.
Mhm.
So if you make probabilistic algorithm and you just multiply 2 probabilities and that's it, and for the rest you use union bound or you add expectations. We did it in approximation in the streaming lecture. We spoke about this. We applied this technique, like transfer to independent hash functions, because we just in many cases we only needed variances. That means we were just multiplying 2 probabilities, and we only needed pairwise independence, nothing more. And so here we can do the same thing, but now we need k-wise independence. And so we will take a set of k-wise independent hash functions, and then try, and instead of taking the probability, we brute force over all choices of the hash function.
Mhm.
And then there's a question, how many hash functions do we have? Do we need for this? And this is kind of good news, because it is order 2 to the power order k, and then there is some, I forgot about the dependence on n. Poly n should be safe here. So that's the number of hash functions we have. And this is very good news, because here we have fewer hash functions than attempts, because t is k to the power k. So if we try all the hash functions, we can, and they're just all the polynomials of degree k we use as hash function. So here we will look, we will map all the nodes n. We will apply a polynomial of degree k. So we iterate over all polynomials so we pick just easy. Take a prime that's a bit larger than n, and then compute modulo n the polynomial. But okay, I will not explain all this. Just saying that it's kind of easy to iterate over all the hash functions. Yeah, it's just generating all the polynomials modulo some prime number a bit larger than k. Okay, but now we are distracted. Well, but since we explained this and it's the second time we use it, we can. Yeah, we can speak about these hash functions. In probabilistic algorithm, they're very popular for the randomizations. Okay, so now let's. So we did this. Now dynamic programming, an easy one. Yeah. So our problem is now a family. So we get the universe. But maybe you should stand. It will help get.
No, my eyes is just tired.
Yeah. So the input is a set U, and then a list of subsets. S1, S2. Till Sn, and they're all subsets of U. And so the question, okay, let us say, so do you understand 2 to the power U? It's
So
all subsets of U.
Power set.
Yeah. So here is a collection C, set U, and then C is equal to this. And the question, can we have a selection of some subsets that covers all of U? Oh, this is strange. It's a very easy question.
Can we have a collection of subsets covers something?
Okay, no, let's
Of a
say,
given size collection.
yeah, sorry, I will do something better. So let's say that, let's not assume they're subsets of U, and then, but it's called set cover. That's strange.
Maybe minimum number of sets.
Yeah, you're right. So let us have some other number. L. Yeah.
Also, if they are not subsets, we can make them subsets.
Yeah, you're right. So yeah, does there exist C prime of C such that so can we select L of these subsets so that all of U is covered by the union? And U.
What is C then?
So C is the set of subsets, the collection of
It's
sets.
2 to the power of
Yeah.
U?
No.
No, or
Yeah,
it's just
I
some, it's
removed
just
the
some
sub-
some
yeah,
collection.
Yeah. Okay. Yeah. I
It's a
realized.
subset of 2 to the power.
Okay.
Yeah. We can add it or not because we're just interested in U being a subset of the union of S and C prime of S. Okay, it's a kind of mathematical notation, but it's clear, right? So can we pick L subsets that cover U? So the problem is called subset cover. Sorry, set cover.
Yeah.
Set cover.
So of course, if the union of C doesn't cover U, no, if the union of all the subsets
Yeah.
doesn't cover U, we can't.
Yeah.
This is obvious.
And so if L is a parameter, then it's clearly FPT because, no, it's not clearly FPT, but our parameter will be the size of U. So here the parameter is size of U. So that means can we have an algorithm that runs in time f size of U times poly n.
What is n?
And number of sets.
Wow.
So, and this is by dynamic programming. So now let's see. if you have an idea.
Well, we can ну просто типа, если S1 покрывает, то нормас. Дальше S1 объединяем с S2, если покрывает.
Нет такого, что это типа очень похоже на предмет.
Ну, типа, да.
Ну,
So the
сложности.
asymptotics doesn't depend on the number of subsets. Not exactly subsets, the size of C.
Yeah, so we can pick L, so C, yeah. So
I
the
think
size of
we-
C can be polynomial dependence, but we can only be, we can be generous with U.
Oh, okay.
So this suggests that we will have something that runs in time 2 to the power size of U, and so we will do something for all the subsets of U. So we need to make a table, and then one argument x. So x will be a subset of U.
Возьмем все формулировки, возьмем эту фигню.
То есть вот это вот, пожалуйста, со шкафчиком.
Then that is. So then usually the table has two coordinates. So what might, okay, I already said what might be this?
Смотри, в X у тебя, короче, 0,1 берем, не берем. А n это просто сколько мы уже отработали? Нельзя так?
Да, не решаю. Сейчас. Еще раз, ну типа. Ну так
Ну,
и
смотри, вот
если
три
0,1,
хода.
то у нас просто строчка получилась.
Че? Нет, в
Ну,
смысле,
0,1. Или ты имеешь в
Нет,
виду
смотри,
типа 2 на n. Ну, у нас n по одной координате, n это число этих чуваков.
Ну, n это просто, короче, сколько мы уже их прошли. Ну, там, условно, не знаю. Прошу и переход, короче. Сейчас, во-первых, мы в первую вставим просто, типа... еще, блин.
Я что-то вообще пока не понял, какого размера таблицы.
Сейчас, я... Размера? Ну как?
Ну да, какие измерения?
Ну, можно там абстрактно сказать, что двухмерное. Но
Не,
на самом
ну
деле
нет, ну
там
я
еще
понял, ну
двухмерное на размер U.
сколько. Ну, так в итоге, типа, сколько...
Ну, размер U плюс 1. Столько измерений.
Да. Слушай, это типа тензор размера модуль U, типа у него модуль U,
Ну,
но...
это огромная херня.
Нет, подожди, у него модуль U это осей или
Ну,
модуль U у него это длина?
Ну, смотри, условно, у тебя в... Ща, блин, как это сказать еще? Я не занимался этим.
5 лет, да, со второго курса.
Is it
Да.
something like a Knapsack
Да,
problem?
всё.
It's
Indeed, yeah. But it's very important. I mean, it's quite often you need to use dynamic programming.
Yeah, no.
At least I need it quite often.
We're not programmers.
I mean, I'm programmer, but I don't use
No.
program.
Okay, it will come if you higher level, if you're supervising, you need to tell your.
I mean, it's just some variant of a knapsack problem.
Yeah. It's also a table.
Ну, смотри, короче, переход. В и G. Это, короче, вот G это, короче, индекс отрезки. SG это мы сейчас нарабатываем. То есть мы либо, короче, TP I это множество. И вычитаем SG, короче. То есть это мы типа взяли. Или мы забили и не взяли. Ща. Да. Вот. Это взяли или не взяли. сначала. Что мы хотим узнать? Ну, это переход. Это теперь макс. И это 1-0. 1-0 храним. Булевин. Это макс. Да, это переход. Согласен?
Ну, то есть это просто типа один на модуль у булевых переменных. Типа, так что ли?
1 на модуль.
Ну, один, в смысле, одна строка, модуль у столбцов. И в каждом...
Сейчас, я это себе представляю, как вот у нас есть S1, S2 и так дальше. И вот это вот... я просто не помню, что столбец, что строка.
Пофиг, не транспонируй, какая разница.
Ну да, ну короче, G, и тут, короче, вот тут.
Так, давай картинку.
Вот тут, короче, либо не взяли, либо взяли.
Ну
Понял?
так вот я
Только
говорю,
это множество.
вот здесь сколько?
Только здесь размерность, да, внутрь U. Размер U.
Ну, то есть, короче, это... Нет, короче,
Вообще,
это трехмерный тензор. У тебя...
Нет, это не трехмерный
А
тензор.
сколько мерный?
Это U мерный в одну сторону, в ту.
Нет, это называется не мерный, это называется, что у него
мерный.
размерность здесь, короче, U, здесь у него размерность, я так понимаю, N.
Ну да, да.
А здесь вот тут у него сколько по вертикали? Ну, у тебя вот
Я
тут
понял,
по вертикали
я понял.
туда и сюда. Тут сколько?
You don't need tensor. Two coordinates.
I don't understand the concept of this table.
I mean,
For now.
Okay, so
Yeah.
So what means T? So we take a subset of U and we wonder whether we can what is minimal number of sets we need among the first and prime sets to cover set X.
да, и здесь еще плюс 1
Yeah.
надо сделать. Yeah.
Костя,
So let me write
probably understood something.
So the table minimum number of sets among
To cover
S1.
X.
S and prime to cover X.
What is
Yeah.
X?
X is this argument.
Yeah, it's
so
a
and
subset
prime
of U.
is here. Yeah.
It's a subset of U, okay. Minimum
And so
number.
now we
Yeah.
so we will do it column by column. So we start with n prime equal to 0. So that's easy to tell what is x 0 here. So if we have no sets, then we can only cover empty set. So it's equal to and then we need 0 sets if x is empty. And let us say plus infinity. Yeah, otherwise. Okay, and now given a column, we want to understand how can we get the next column.
What does N prime stand for? What is N prime?
And prime here. So we can only use the first n prime set.
Out of C, right?
Yeah, out of all n. So we order the sets.
Okay.
And
See, so
now we want to know what is tx
1.
n prime plus 1.
It's minimum, of T X without X minus S and
Prime.
yeah,
Okay, let's do it like this.
yeah. And
N prime.
yeah, minus 1, yeah, and just T X
Plus 1.
yeah, plus 1, and T just X and N minus 1.
Yeah.
And
Right.
prime minus 1, yeah.
What is the second coordinate once?
So n prime tells you that we can only use the first n prime sets.
Yeah, how much we already have.
Yeah.
Okay.
And then to know, so what is the task? Cover x using the first n prime sets with minimum number of sets. So it will
What
be, this
are
will
the
be a
definition?
number.
Am I right that the dimensions of the table are 1
Yeah.
or 1 by n?
2 to the power u times n will be the table, the size of the table. So x is a subset of u.
Yeah.
Yeah.
How do we take minimal then?
So we take the best way, so the fewest sets we want. So the table will have a number. So a number which is at most n prime if we use all the sets, and at least one, unless x is empty. Then yeah.
Okay, so you take the min.
And so our task is cover x. And so there are two cases. Either we take set n prime, and then we are in this case. So then we need other sets to cover x minus Sn prime.
Yes.
Or we don't take x n prime. And then there's this case. We need to cover x with all previous sets. And so this is the minimum number of sets we need to cover x, not using Sn prime.
What is in the table? Like what is written in the table? Like we
Yeah. What is the best number of sets we use? So here is what is written. So I wrote it in words here. Minimal number of sets among S1 till Sn prime to cover x.
Okay, it's a number.
Yeah, it's number.
Each cell has a number.
Yeah.
Cells are indexed in like how? And the columns are indexed by integers from 1 to n prime.
Yeah.
The rows are indexed by what?
Sets.
By sets.
Subsets of u.
By sets. Okay, so we can just renumber them with integers from 1 to u to the power of this. Okay. Now what do we write in the cell? Like zero plus infinity, and then the transition function comes into play.
Yeah, and then in the end, of course, we look to u and n, and it will be our answer.
Tak, okay. Minimal t
So for each subset of u we have a column.
Yeah, a row for each
row.
subset of u, a row.
Okay.
Great. Good.
Oh, useful lecture.
Yes. Very useful.
At least I think it's useful. So this is dynamic programming. We will use it again for the last step if we get there today, maybe next week. Well, probably next week. Next one is branching. And so there is a feedback vertex set problem. It's like in all the books about parameterized complexity, so I will honor all the other teachers, and I never needed this problem. But okay, it's kind of nice. So the input is now a graph again, and the question is, how many vertices do we need to remove to get a tree? So it's called the feedback vertex set problem. Like feedback refers to cycle. If a cycle happens, like there are microphones or something, if there is a cycle you can have beeping. If it's a reachability graph, that's kind of directed problem, it's undirected variant. So input is a graph and number k. Question, can you remove nodes to get a tree? Oh, let's do a little other exercise. So you remember branching. So the problem, it's in the exercise list. So number 4, no.
Triangle packing.
No, that's with coloring. There was another thing with being triangle free. Can you remove k points to get a triangle free graph? Here, the third exercise. So show that the problem is FPT, just to remember from last week. How would you do it? So can you remove k nodes? And now you end up with triangle free graph. So it's another problem. Here you want a tree, but let's first think about triangle free graph. How will you do it?
Remove keynotes.
So how can you prove it's an FPT?
We did something with to remove not triangles, but
Yeah, indeed,
triangles
you're
without
right.
one.
So you need to do the same thing. So to get, we can get an algorithm that runs in time 3 to the k poly n. It's called branching technique.
Yeah, we branch like that. We pick a node, we either remove it to the left or we remove all its neighbors.
Yeah, so we search for triangle. If there is no triangle, then we know the answer.
Yes.
Triangle, yes.
Mhm.
And if there is a triangle, then we try to remove each of the 3 nodes.
Mhm.
And so we decrease k by 1, remove one of these nodes, and then repeat.
Yes.
And so, and then the recursion tree each time splits into 3. And since k decreases in each recursive level, the depth is k, and so we get this runtime.
We need to remove exactly k nodes or less than k.
At most k
At
nodes,
most.
but in the worst case, each time we
you
remove
will
k.
remove more
No,
Remove
we-
more.
we-
if you want.
No, we can't. We can
If,
do
I
that.
mean, if you can do in less than k nodes, you can remove more. Your question was.
Yeah, okay.
Yeah.
Okay.
Okay.
Okay, I got your point.
And so now here is let's go back to our problem. So we will make a branching algorithm like this. But okay, I will just tell you what's the answer, because there is no chance you can guess the lemma. I mean, okay, I should be careful. So I will tell the lemma, you can tell the algorithm. So lemma is, so let's sort the nodes by decreasing degree. V1, V2, and the degree is D1 bigger than D2, and so on. And then the claim is that among the first 3k nodes, there is always a node inside, so every feedback vertex set contains at least one node among the first 3k nodes. This is the lemma. Lemma, every feedback vertex set,
Feedback vertex set is like
a set of k nodes that you need to
that
remove.
that have a cycle, or no?
No,
No,
it's the set of k nodes that you need to remove in order to obtain a tree. It's called the feedback vertex set. Okay, let us do this again. So this graph has feedback vertex set of size 1.
Which is
Yeah, okay.
left top.
Yeah,
Top
Or
left,
right.
top
yeah,
left,
we
top.
just,
Doesn't matter.
no, the top doesn't work.
I mean
Yeah.
top left.
Yeah,
top
yeah,
right.
yeah, yeah.
Uh-huh.
Okay.
Okay, every feedback vertex
So
set
I
is
don't say tree, no, it should be the forest, so cycle free. Because, I mean, the graph might be disconnected afterwards.
every feedback vertex set
Set.
is where? Is what?
Contains a node from, so at least one node from V1, V2 till V3k.
How do we sort the nodes?
So by
decreasing
decreasing degree. So
decreasing.
among the 3k nodes with maximal degree, there will be at least one in every feedback vertex set. Ah, wait, it's not true. If all degrees of the graph is at least 3. If every, if graph connected, I'm not sure. Okay, anyway, if a graph has, if each node in graph has degree at least 3, at least 3. Then every
But what if we have degrees?
2 nodes, we will use kernel, we will use reduction rules.
Okay.
So, okay, so to state the reduction rules, let's use multigraphs. It means that, multigraphs it's called. Nodes can have, 2 nodes can have parallel edges. Otherwise it's very hard to
nodes
state
are
the,
stacked.
edges can be stacked. So we say these 2 edges are connected 3 times, 4 times, and so on. And we allow self loop.
This is the first time
Yeah.
I see the problem when self loops are allowed and
Yeah.
it's allowed to stack the edges.
Very useful lecture.
No, it's actually quite a technique.
Yeah,
I
but
remember I
otherwise,
even used it to solve it.
yes, but otherwise to state the reduction rules, it's hell, and I guess to program also hell. Okay, so what will be the reduction rule to get rid of nodes of degree 0, 1, 2? So remember our problem here. So we don't want to change the answer and just get rid of nodes.
So we can add some additional nodes that that just duplicate the existing. We can add some additional edges that just duplicate the existing edges.
Yeah, if you want to go to normal
Some
graph,
mock edges, so we increase the
the number of nodes.
power of each node.
Yeah, but now I tell you, you're allowed to have the double edges between 2 nodes.
Yeah,
Or
you just
triple, yeah.
or we can just add self loops for each of these.
Yeah, but we need to do, to get rid of degree 3 node, add self loops everywhere.
Yeah.
Yeah. Okay, I didn't anticipate this. Okay, good point. It was not the answer from the book.
But if we are allowed to have self loops and we can have 2 similar edges, does this lemma work in this case?
Yeah, you're right. So here we cannot have self loops. The multiple edges, I don't know. We will need to check the proof. It's allowed multiple edges.
Okay.
So but the self loops, no. So we need to.
So if we have if the node has a power 0, we don't care about this.
Yeah, we just throw away the node.
Yeah.
So reduction 1, delete isolated nodes. Reduction 2.
So if the power of the node is 2 we take any 2 or 1 we take any of the of the edges that are connected to this node and just duplicate them
Yeah.
as much as
Okay,
we
let's
need.
call it 0 because the degree is 0. Let's write it separately. When the degree is 1, oh no, we can merge these. Delete isolated nodes and nodes of degree 1.
Yeah.
They cannot be in a cycle, so irrelevant. And
So
then
the reduction
second
will
rule-
just pretty.
yeah, it's easier. And then the second rule,
So
no, the nodes
there
of
are
degree
the
2.
rule number 2. We just take all the nodes that have degree 2 and
Yeah. Remove
adds-
it.
Why remove?
We need to get rid of these
Oh.
nodes.
Okay.
But if we
Sorry
remove
for
it, it's-
interrupting.
No,
Just
no.
listen to.
no, yeah, tell your idea.
Yeah, my idea was just to add any of the edges that these nodes have and just have multiple edges between. For instance, we have this.
Yeah, I see what you're trying to do. Yeah, let's add an edge.
Yeah,
here,
yeah.
and then we have 3. Yeah. Okay, we
But-
will need to check about multiple edges, but let us say in the book, I don't remember, I cannot tell right away if it works with multiple edges or not. It means I'm a bad teacher, I should go through the proof in 1 second. But I had trouble to prepare. So the plan is to remove the node and put an edge here.
Okay, it probably works.
Yeah, it doesn't change anything.
Yeah. Indeed, it doesn't change anything. But that's why we need multiple edges. Okay, we cannot, sorry, your trick doesn't work. No, now I understand. So what here, let's do this here, but then if you have double edge, it is actually a cycle. And then we change the answer. That's why we cannot do it.
Okay, I see.
Yeah. It's
We
like what
probably
is
don't
definition
even,
of cycle? Yeah, it is a bit tricky. And here we see what's happening. Like if there is already an edge, we delete the node,
And
we
don't do
create
anything.
a second edge.
Why do we need to create a second edge? If we create a second edge,
No, if we just delete this node, we are deleting a cycle and we might change the answer.
okay, I see.
So that's why we need double edges.
So yeah, we want to leave the cycle
Yeah.
when it was in the initial
Yeah.
graph.
Delete node of degree 2. And insert edge between neighbors. And here we only need to do it if there is at most one edge. If there are already 2 edges, we don't need to create a 3rd edge. But okay, it doesn't matter for anything. And that's it. And so after we do this, then we get the graph of degree, where all nodes have degree 3.
Every physical vertex set contains a node.
It contains a node from the first 3 of degrees.
3K.
3K.
Yeah.
Oh.
Okay, now let's check about self loops. So what can happen? Oh, if we have a node like this, whatever, and here are more things in the graph, then we have a node of degree 2, and so it has 2 times the same neighbor. So when we delete this node, we need to add a self loop here. So we need to allow self loops, and now let's hope the proof of the lemma works with self loops. Okay, I think it works.
So now
But if it works, we can just add self loops in the first place.
No, but then you change the answer, because a self loop is also a cycle. Okay, good. Yeah, that's a good point.
this is not for what the self loops are needed.
Yeah, yeah. but that's how it happens. So imagine that there is a triangle, or graph is a triangle. So what will happen by the rules? We will delete a node and add a circle here. And then we will do the same thing here. We delete this node, but we need to add a cycle here. Okay, and in this case,
So this lemma works only in certain scenarios of self loops.
yeah. So we need to keep self loop and parallel edges.
But why not? The lemma works, but if we use the self loop in an incorrect way, so the lemma, so the graph changes and the answer changes.
Yeah. If you just add self loops, it changes the answer.
Yeah.
So we receive the graph that is not equivalent to the initial graph.
Yeah, because I need to be careful what is cycle, and so self loop is a cycle, and parallel edges, two parallel edges also.
What is the degree of this node?
It's 2.
2, okay.
So in this
So
case,
if it was 1, we would just
yeah,
delete it. Like immediately.
yeah. So, but if everything contracts to a single node, so we need a third rule. Like if we have such nodes, then we delete it and remove k, decrease k by 1.
Okay, now we want to do some branching.
Yeah. Yes.
So we take, so I think at the first step we just iterate through each of these 3k nodes and do a recursive call.
Yeah. So we add them to the vertex cover, so it means each node we remove it from the graph and decrease k by 1 and then recurse. And we do it for all these nodes. So what will be the runtime? Is it an FPT?
3k factorial, probably yes.
Not factorial, so we will have a branching, so that there will be a tree, and in every node, how many branches?
3k.
No, sorry, you're right, 3k factorial. No, you're not right.
Something like, but not exactly.
So in the first node, we have 3k branches, and then in the next node,
k minus 1 for each of the 3k nodes. Okay.
so in each node there are 3k branches, because in each so we remove a node, but then we get a new set of 3k
But
branches.
we have another, the k changed, no? The
You're
the
right.
k
The k
reduces,
decreases.
decreases
Sorry.
by
Yeah,
one.
you're right. 3k factorial is the depth. My fault. 3k factorial.
No, the depth is just 3k.
Yeah, but the size is 3k factorial, because number of children multiplies in each level by first times 3k, then times 3k minus 1. Yeah, a good point. Yeah, I was wrong. 3k factorial, yeah. Okay, you're good with branching algorithms. So you've done this one.
Gentlemen, let's take a break.
Yeah, but it's time for the break. So then we will do exercise.